Good day, everybody. Today we're going to look at making an angle function that'll work on the entire xy plane. This is helpful if you're studying polar coordinates, and it also is kind of a potential function for a particular vector field. So if we have a point in quadrant 1, then it's kind of easy to figure out what that angle should be. Like here I am, if x is 2, y is 1, we're at the point 2, 1. Opposite over adjacent, 1/2. Tangent theta is 1/2. Theta is arctan of 1/2. But in the other three quadrants, we don't necessarily have the angle we want using arctangent. So let's just see. The way we're probably supposed to get it is using reference angles, which I have here. And of course, quadrant 1, you've got a reference angle equal to the actual angle. But if, say, I look in quadrant 2, then still opposite over adjacent, if you just think of that triangle as 1/2. And so the reference angle would be the same, arctan of 1/2. But now you can see if we're in quadrant 2, the true angle is pi minus that reference angle. And so in radians, there's that value. Or if we're in quadrant 3, again, the triangle still has opposite and adjacent 1, 2 in absolute terms. So the reference angle is still arctan of 1/2. But now the angle with the positive x-axis is pi plus the reference angle. So you have to use just a little bit of knowledge. It's not too hard, but knowing what quadrant you're in, you can get to the actual angle. Finally, if we're in quadrant 4, again, the reference angle, if opposite is 1, adjacent 2, so this would be 0.2, -1. But now, generally, we want angles from 0 to 2 pi. So if you find the reference angle, arctan 1/2, you want 2 pi minus that reference angle. So you can think that way. Now, sometimes you do want a negative angle in quadrant 4. Then arctan of -1/2 does give you the correct angle, but it's going to give you a negative angle. So if you want angles from 0 to 2 pi, you can't do that. So just a little bit of thinking will get you your angles. But if I can do it as a human, why isn't there something that I can input the xy's and just output the correct angle? It seems like there should be. Well, we can't do it with just one value. I mean, part of the problem with arctan is if I look at the graph of tangent, right, the tangent will equal 1 infinitely many times. And so trying to do the inverse, if you switch x and y, you get kind of this graph. Now this isn't a function, it doesn't pass the vertical line test, so we pick the main branch right here. And so we can take the arctan of any real number, but we're going to get either an angle in quadrant 1 for positive x here, or negative angles for negative x. Okay, so we just take this main branch. There's the arctan function. So here is the arctan function, and it works for quadrant 1 and quadrant 4 as long as we are okay with negative angles for the arctan of a negative number. To generalize this, we're going to think about complex numbers. And we can think of them in two ways, x plus I, y. So you go a certain amount x, a certain amount in the y. Label it like that. But you can also, again, kind of a polar form, think of it as r e to the I theta. So either way to get to that point. So if I square, what I'm going to get is the distance is now r squared away, where before it was r. Do it here. And then the angle is going to end up being double. So here's a little picture. So I started with the point AB, or A plus BI. If I square it, and this was root 2 away from the origin, then now the new point is 2 away from the origin, and the angle is double. And if the point AB was in quadrant 4, using negative angles, and if I square it, then this angle is now double that negative angle. And again, R was root 2, and now this distance is 2. And so I'm essentially going to square, and then every point in quadrant 1 or 4 with angles like this. So arctan, you have points where x is greater than 0. If you square that, you're going to then cover the entire xy plane except the negative x-axis. Okay, so before tangent theta equals y over x, or arctan of y over x, wasn't defined at x equals 0, the y-axis. Squaring that, it's still not defined at this ray, but it's defined everywhere else. So we made a big improvement. So let's see what we gain. So I want to fix x plus iy, and then find a plus bi, so that a plus bi squared is x plus iy. And well, if you square it, I'll skip a few of the steps, you'll get a squared minus b squared plus 2abi x plus iy. So we've got kind of two equations. We've got, for the imaginary part, 2ab must equal y. And what I know is that a is greater than 0. Okay, so I want to, for any point in the plane, except on maybe this negative x-axis, it's the square of some point on this half plane, the right half plane. So a is greater than 0. So what I want to do is solve for a. So to do that, I'll actually first solve for b. So b will be y over 2a, and then substitute this into the real equation. The real equation is a squared minus b squared. I'll substitute in what b equals, and that has to equal x. So let's multiply through by 4a squared. So that'll give me 4a to the 4th minus y squared equals 4a squared x, which actually a is my variable, so I'll put the x right here. Move everything over. 4a to the 4th minus 4x a squared minus y squared equals 0. So we can solve for a squared. A squared will be negative b, which will be 4x, plus or minus the square root of b squared, and that'll be 16x squared, minus 4a, which will be 16c, which will be negative y squared. So 4ac will be plus 16y squared, all over 2a, 8. So a squared will equal 4x plus, I can lose the minus because this is going to be bigger than 4x, and a squared is a real number. A is a real number, and a squared is a positive real number. So I can't have a squared negative. That would make it imaginary. So plus, pull out the 4, or 16 rooted 4, x squared plus y squared all over 8. So this just ends up being x plus the square root of x squared plus y squared all over 2. And now I can take the square root, and this is why I chose a. So when I said solve for a, and then this is what I meant. A, I know a is positive. B could be positive or negative, but a is positive. So it was good to solve for a. So I know a has to be the positive root x plus the square root of x squared plus y squared all over root 2. Just take the root of both sides. Now b, go back to here, b is y over 2a. So that will be y divided by 2a. Let's just flip and multiply here. It'll be 2 square root x plus square root x squared plus y squared. And this root 2 flips up on top, so I'll put it like that. So now I have the coordinates. So again, if you give me any x and y in the plane, and they could even be in quadrant 1, so I could have xy here, or I could have xy here, or I can have xy here. Get the idea. Xy anywhere except on the negative x-axis. Notice there's trouble on the negative x-axis. I've got this denominator of 0 if I'm on the negative x-axis, because this is bigger than x squared unless y is 0. And then it equals absolute value of x. And so if x is negative, this will be 0. So trouble on the negative x-axis. Anyhow, so for any point anywhere in the plane other than that, the point AB, whose square will give me this, will be in either quadrant 1 or 4. Right, so this A possibly might square to this point, and so forth. That's AB here. These will be the coordinates. And well, I can find the angle in quadrant 1 and 4 just by using arctan. Angle for AB. We draw it here just to a single one. Let's say that's AB. But remember, XY was actually picked first. Say it's like that. So if you pick an XY, you can find the AB. And then I can find that angle to AB. Call this theta AB. Well, that'll just be the arctan of B over A. That works. And in terms of X and Y, this will be arctan of B, y root 2, 2 square root of x plus square root of x squared plus y squared, divided by A. We'll flip and multiply here. Root 2 over the same thing, x plus square root of x squared plus y squared. So this will just end up being arctan. Root 2 times root 2 is 2, which will cancel that 2. So y, and then these are identical, so they'll multiply together and just give me x plus the square root of x squared plus y squared. So that's the angle to AB, and then angle to XY, so theta for XY, will just be twice the angle to AB. So 2 arctan y divided by x plus square root of x squared plus y squared. Now the range for that will be negative pi to pi. Negative pi is less than theta of xy less than pi. And so you've definitely expanded, but we still left off, but hopefully you can still figure out the angle yourself. If you've got some point here, say at negative 3, 0, you can figure out the angle. Usually you'd call it pi instead of negative pi. So if you're on the negative x-axis, know the angle is pi. So related to that, generally we want angles from 0 to 2 pi. So there's different ways we can get to that. I'll just redo the same work and derive it from scratch. First note, we can use arc cotangent to get any angle in the upper half plane. Right, so obviously in quadrant 1, instead of y over x, it's now x over y, kind of adjacent over hypotenuse, or adjacent over opposite. Then the arc cotangent of a negative will give us a angle in quadrant 2, from pi over 2 to pi. Quick look, the graph of cotangent looks like this. And so if we invert it, here's the main branch. You know, you always want the 0 to pi over 2 portion, and we prefer a nice continuous function, so the other part we'll take is this. So here's the graph of arc cotangent. So again, the arc cotangent of a negative will be an angle between pi over 2 and pi. And so overall, the range of arc cotangent is 0 to pi, open. Note, should draw the triangle probably, but if you draw a triangle, so here's a hastily made right triangle, and if we look at, say, this angle, it would be arc tangent of x, opposite over adjacent would be x. This other angle would be arc cotangent of x, adjacent over opposite. So arc cotangent of x plus arc tangent of x, these two angles add up to pi over 2. So you can see it in acute right triangles, but we can also use calculus if you like. If you know the derivatives of arctan and arc cotangent, then you can show the derivative of their sum is 0, and then if you evaluate at any one point, say 0 most conveniently, you get pi over 2. So if the derivative is 0, the function's a constant, and so it must be pi over 2 for all x. So arctangent plus arc cotangent is pi over 2. So if you don't like using arc cotangent, don't have it on your calculator, you can just do pi over 2 minus arctangent of the same argument. All right, so there's the upper half plane. Well, now we're going to square that, and here are examples of a point AB being squared. AB is different points in the upper half plane. If you square it, then you get the lower half. But so, and conversely, if you fix XY, there'll be some AB in the upper half plane that takes you to that, except on the positive x-axis now. That we don't have. So the range of theta will be 0 to 2 pi. So arc cotangent of x over y, you can't have y 0, so it's not defined on the x-axis. But when we square it, now it won't be defined on the positive x-axis. So again, fix any point, find a plus bi, so that a plus bi squared is x plus iy. So we'll get a squared minus b squared plus 2abi has to equal x plus iy. 2ab must equal y as before. But now what we know is b must be greater than 0. Right, so we're going to have some ab here, a plus bi, b greater than 0. So since that is known, let's solve for b. And to do that, well, we first solve for a. So a will be y over 2b, and so that's from the imaginary parts, putting them equal to each other. Now if we look at the real parts, we'll have a squared minus b squared has to equal x. And so this will give us y squared over 4b squared minus b squared equals x. Multiply through by the 4b squared. Move everything to the right-hand side. And again, use the quadratic formula to solve for b squared as our variable. So it'll be negative b plus or minus the square root of b squared minus 4ac. So 4a is 16c minus y squared. Gives me that all over 2a. So it's similar to before, well, 2a, so we'll call that 8. Again, b squared's positive, so we have to take the positive root. And I can factor, so I'll do it on the next line here. Because otherwise b squared would be negative if I do the subtraction. Factor out the 4, so that'll be negative x plus the square root of x squared plus y squared all over 2. And again, b is positive, which it will be. B squared's positive here, or it could be 0, but it's not negative. So I can take square roots of both sides, and I'll take the positive root again. Kind of like to subtract after the fact, so let's put it as square root of x squared plus y squared minus x all over root 2. And again, we can then solve for a, y over 2b. So since a is y over 2b, this will be y, we'll flip and multiply, to square root of x squared plus y squared minus x, and bring this root 2 up, so root 2. And again, just like before, we can now get the angle to the point AB. It'll be, now we'll use arc cotangent of x over y, so that'll be a over b, I should say. Right, so if I want this a, b, could be in quadrant 2. But, so that angle, arc cotangent, will give me that. Maybe put a second AB here, but so no matter where the point is, as long as it's in the upper half plane, this will give me the right angle, and then 0 is less than or equal to, I'll put that here now too. Let's put it in terms of x and y. So a so that's readable, but I have it typed or not, whoops, and then times, I guess I'll put extra parentheses here, so times the reciprocal of b. So if I multiply by that reciprocal, we'll get root 2 over the essentially same denominator, but without that 2. So that product, so theta of AB will be the arc cotangent. Root 2 cancels with that 2. So y, this times this, squares it out. So I just get square root of x squared plus y squared minus x. And again, you see there's trouble on the positive x-axis, but nowhere else. So as long as y is not 0, you're good. And then if y is 0, you're only in trouble for positive x, because then you'll be dividing by 0. But at negative x, you won't be dividing by 0. And then the actual angle to the point, so if we had xy first, and we found the AB, whose square took me to that. Let's see, this square will take me to there. No, that'll take me to here. So somewhere around here, say like that. Anyway, this will be double that angle. So this will just be 2 arc cotangent y over this square root minus x. And we can also, again, if you don't want to use arc cotangent, you can do 2 and then pi over 2 minus arc tangent of the same argument. So that would be the angle. So here's our results in typed form. So if you want an angle from 0 to 2 pi, which most of the time we do, you can use either of these two top formulas, and then it works for any point not on the positive x-axis. So here's some sample xy's. So for any point, this will give you the decimal value. Some sophisticated math software might even return the proper angle of, if it's a multiple of pi, say you had like negative root 3, negative 1 as your point. Or we can use this formula, but then the angle goes from negative pi to pi, so it depends. And then but it works for all points not on the negative x-axis or the origin. So we've got a couple options there. Last thing I will mention is for the potential function. If you take the gradient of arctan of y over x, do that second here, do the details too carefully here, but you get negative x squared plus y squared, and x squared plus y squared. So this is a popular vector field, which is kind of not conservative, although it sort of has a potential. You just have to only stay on the domain of definition. So arctan would work if you don't leave the right half plane, and arc cotangent would work if you want to stay in the upper half plane. Well, now we have bigger domains, so, and it's worse to check the derivatives, but if you take the x partial and the y partial of, say, this function, so if you went from 0 to 2 pi, you will get the proper result for the x partial, obviously a lot more messy, and the proper result for the y partial. So it's a potential, but you've got sort of a line of that you can't cross. But for curves that don't cross that line, you can use this as a potential. Or you can use the arctan one, so this one with the range negative pi to pi. This works. So again, if you want to do all the gory details, the x partial and the y partial. All right, so we have a function that works just about everywhere to give you the correct angle for any point in the xy plane. Hope you enjoyed this and have something to ponder for the rest of your day. Thank you.